Hi there, welcome back to our channel. We are continuing with the fundamentals of electric circuits. In this video, we are going to take a closer look at the most basic circuit configurations and maybe mention two much complex circuit configurations to spark your curiosity and how they affect voltage, current, and resistance in the circuit. While at it, we will also talk about the fundamental laws used in circuit analysis. All right, let's get to it. The first circuit configuration is the series configuration. As mentioned in the previous video, in a series configuration, components are connected end to end such that there is only one path for the current to flow. This means that the same amount of current flows through each one of the components that make up every given series connected circuit. The total supply voltage of the circuit is divided in proportion to the resistance of each circuit element. The circuit elements with larger resistances have larger voltage drops across them than the ones with lesser resistances. Say you have circuit made with a voltage source of voltage V, the total current through the circuit is I, and two components of resistances R1 and R2 in series. To determine this voltage drop across a component of a certain resistance R1, you use voltage division, which says VR1 equals R1 divided by R1 plus R2 multiplied by V, R1 being the resistance of the component whose voltage drop you are looking for. The total resistance of a series connected circuit is simply the sum of the resistances of the individual components in the circuit. R total equals R1 plus R2 plus R3 and so on until the last component. The second circuit configuration is parallel configuration. In a parallel circuit, components are connected across the same voltage source. This allows multiple paths for the current to flow. Also a description given in the first video of this series. I will leave the link to that video in the description below. The supply voltage is equal to the voltage across all the circuit elements in the circuit. The total current of the circuit is divided in an inversely proportional sense to the resistance of each circuit element. The circuit elements with larger resistances have lesser amounts of current passing through them than the ones with lesser resistances. Say you have circuit made with a voltage source of voltage V. The total current through the circuit is I, and two components of resistances R1 and R2 in parallel. To determine the current through a component of a certain resistance R1, you use the current division, which says IR1 equals R2 divided by the R1 plus R2 multiplied by I. R2 being the resistance of the component through which the current you are looking for is not passing. The reciprocal of the total resistance of a parallel connected circuit is the sum of the reciprocals of the resistances of the individual components in the circuit. 1 over R total equals 1 over R, 1 plus 1 over R, 2 plus 1 over R3, and so on until the last component. Now, what if there were three resistors, R1, R2, and R3 in parallel? How would you determine the current through R1? Leave your answer in the comment section. I will provide the answer in the next video. These two configurations can be combined and make up a circuit that has both series and parallel connections. When this is the case, you simply break down the circuit into sections and deal with one at a time. You can focus only on the parallel section and determine the total resistance of it, and then use that total resistance as a resistance of a component that is now in series with the series section of the circuit. And voila! You have a series circuit. Now, let's talk about three of the most basic laws that are used when analyzing an electric circuit. They are Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. With these three laws, you can analyze any basic electric circuit. Ohm's law was already alluded to in the first video of this series. It states that voltage equals current times resistance, or V equals I times R. This means if you know two of the electrical quantities, you can easily determine the third using this relationship. For example, if you have the supply voltage and the total resistance in a circuit, you can determine the total current through the circuit. Similarly, if you know the voltage across a component and its resistance, you can determine the current passing through that component. Kirchhoff's voltage law, KVL, states that the sum of all the voltages around a loop is equal to 0. For example, say you have circuit made with a voltage source of voltage V and two components of resistances R1 and R2 in series. KVL says source voltage plus voltage across R1 plus voltage across R2 equals 0. Or negative V plus VR1 plus VR2 equals 0. The sign of the voltages depends on the polarity of the terminal that the current uses to enter each component as it flows through the circuit. Remember, in circuit analysis, we use conventional current, and therefore current flows out of the positive terminal of the source and into the negative terminal. However, it flows into the positive terminal of other components and out of the negative terminal. The last basic law is Kirchhoff's current law, KCL, which states that sum of the currents entering and leaving a node is equal to 0. A node is a connection point of components in a circuit. Say you have circuit made with a voltage source of voltage V, the total current through the circuit is I, and two components of resistances R1 and R2 in parallel. KCL says that the total current I plus I1 plus I2 is equal to 0, or I minus I1 minus I2 equals 0. The sign of the currents is dependent on whether the current is leaving or entering the node. If you choose the currents leaving the node to be negative, which is what I did, the currents entering must be positive and vice versa. So far, we've only spoken about voltage, current, and resistance. However, there is still electrical power. If you want to know what that is, check out my first video on the fundamentals of electric circuits. Okay, now if you know or have determined these three quantities we've dealt with so far, you can determine the power of any of the components in the circuit. You can determine the total power in the circuit using P equals V times I, P being power, V being source desired supply voltage, and I being the total current through the circuit. You can also determine the power consumed by each component using the same formula, except in the case of components, V will be the voltage across the component, and I will be the current through it. You can also determine the power consumed by the component using P equals V squared over R, or P equals I squared times R. R being the resistance of the component. Lastly, sometimes a circuit can neither be connected in series nor parallel nor both. You will see a connection that looks like a letter Y or delta. Sometimes the Y connection looks like a T and the delta connection looks like the number pi. The Y and the T connections are the same thing, and the delta and the pi connections are the same thing. The connections are mostly found in three-phase applications like power transformers and electric motors. Other applications include electric filters and many others. This is a concept we will further explore in detail when we discuss three-phase circuits. Now let's consider a simple circuit project you can try at home. You can create a basic LED circuit using a 5 volts battery, two resistors different values, e.g. 56 ohms and 60 ohms and 500 ohms and 560 ohms, and two LEDs. First, connect the battery in series with one resistor, the smaller one, and one LED. Note the brightness of the LED. Do the same with the larger resistor. Disconnect the battery from the larger resistor series circuit. Reconnect a resistor, smaller, and an LED in series. Connect this series connection in parallel with the series connection that you just disconnected a battery from. Reconnect the battery in parallel with the parallel connection of the series connections. Tag or share with a friend that you would like to do the project with. Leave your observations in the comments below. Thank you for joining us today. If you found this video helpful, don't forget to like, subscribe, and hit that notification bell for more content on electrical concepts. If you have questions or topics you'd like us to cover next, leave a comment below. Until next time, keep experimenting and stay curious. Bye.